It's hard to describe. It's like your phi is allowed to go like this. Your theta is allowed to go like this. So it's like that. See me doing that?
Triangle?
And then your rho can go out like that. It's weird. It's weird. I just showed you. There it is. That's what it looks like. Actually, forget which one's which. Okay, hold on. Nope, this one. There we go. Let's kind of look at it from the perspective that I was standing in the room. So that's me standing in the room, facing to you, like that. So I'm facing you like this. And what I'm saying is my phi goes between two things, right? My theta goes between two things. And then my rho is the in and the out. Do you notice on this front side right here, it's curved in, right? It's curved in. And on the back side, it's curved out because it's two spheres, an inner sphere and an outer sphere. It's cool, right? That is a spherical box.
You know what that looks like?
What?
The pineapple slice? Yeah. You know, when they cut it up?
It's not the way my wife cuts them up. But yeah, you know what? You know what? In some sense, yes, I think I do agree.
Sort of.
Yeah, sort of. Oh, that has a curved look to it. It's interesting, yeah? Okay, so we need to know if our solid looks like this, then how do we do an integral, right? So we need to first know, how do you convert from Cartesian to this system, right? How do you go, because we knew how to get from Cartesian to polar, right? And then Cartesian to cylindrical was pretty easy because we just did the x and y, we did polar and left the z alone. But how do you go from Cartesian to spherical and back and forth? What are the connections? This right here is just that same animation. Oh, I need to say something first about phi. So here's your phi. That was you pointing up and down. The restriction on phi, we do have some restrictions here. Phi can only go from 0 to pi. Not all the way around. 0 to pi. Because imagine if I go from 0 to pi and then start swinging around, right? 0 to pi. I'm back, right? Through here, back, all the way around, all the way around. I get the entire sphere. If I went all the way with phi, all the way back, then I couldn't go all the way around because I would go overlap myself. So the convention that we use is that we restrict phi between 0 and pi, and then we let theta go all the way around. And then rho can, be whatever. So here's the formula I guess you need. The thing that's most important to you is this right here, how you convert. All right, x is equal to, look at that right there. Does that look familiar?
Yeah.
That's polar, isn't it? Except instead of r, we're using rho. R cosine theta. Ignore that. How about the y? R sine theta, rho sine theta. So that part's the same, but what do you tack on to the end of each of those? Sine phi. You can say phi or phi. Okay, it's debated, all right? Sine phi is tacked on to, so it's your polar with x and y, right, with the additional sine phi. Now, the z is different. The z becomes rho cosine phi. And then, you know how we had r squared was equal to x squared plus y squared with polar? Rho squared is equal to x squared plus y squared plus z squared. And then this is where I say, the theta can go all the way around, Your phi is between 0 and pi, and rho just has to be positive or 0. Then these conversions work. All right, we're not going to do any practicing of converting from one system to the other in terms of like, hey, take this point and change it to spherical. We're going to get right into the integrals. So when we use polar and cylindrical, what was the thing when we set up the integral that we couldn't forget? The r, right? The r was there. And I tried to show you geometrically where that r came from, but I think I was somewhat successful. It had to do with an arc length or something like that. After this section, we're gonna actually get to see where it actually comes from, all right? So just like with polar, there was the r we have to remember. With spherical, there's something we have to remember to put in there. And here it is. That's too big now. Yeah, okay. So when we set up a triple integral in spherical coordinates, we will have to take our function. We will have to replace x with this, replace y with this, replace z with this. And then it's not just rho that goes in there, it's rho squared sine phi. It's an entire expression in there. It's pretty complicated, actually. But we have to remember to put it in anytime we go from Cartesian to spherical. I will try to show you where that comes from today. I may have time to actually show it. And then here the order of integration doesn't matter because the spherical region I'm looking at, everything's between constants. Okay, everything's between constants, so we just change that order if you want. Just can't forget to put the rho squared sine phi. Every region that I'm ever going to look at in spherical coordinates in this class, I mean, we're almost done. This section, we're going to be done in 5 minutes, 10 minutes. Your restrictions on your theta, phi, and rho will always be between constants. We won't go any more complicated than that. But you can imagine, you could have, your rho be two functions of theta and phi. Yes?
Is phi the one with the P symbol?
Yeah, no, okay, so this is a rho.
Okay.
This is rho. Yeah, the Greek letter is a little weird. So this is the way that my computer system does rho, right? Don't confuse it. That's sigma and then rho.
Okay.
Yeah. Yeah, phi is this one.
Okay.
Yeah, that's what you were asking, right?
Yeah.
Sorry, I had a cat named Ro, and his sister's name was Theta. Anyway, I'm not a cat person, but my best friend, his wife was one of those people who would pick up animals on, strays and bring them in. She brings a stray cat in, and it's pregnant. And they already had like 4 dogs and like four dogs and 4 cats in their little 1-bedroom apartment. So it had like 8 kittens, and they're like, will you take one? I'm like, I don't like cats, man, And she convinced me. I took one, and then after a day, I was like, no, you need a friend. So I said, give me a sister or something. So I had my 2 cats, Ro and Theta. Anyway, so I was thinking about Ro. I forgot what you were even asking. So this is phi, right? This is phi. Don't confuse phi with the empty set. So phi actually is not written this way. It's hard to see it. It's more, hold on, that's no good. Here. I don't like the way this computer does phi, but, I don't get to choose. There. See it right here? So this is capital. That's capital phi, lowercase, the Greek letters. Okay, so it's like this. golden, what? Golden ratio? Yeah. It's the golden ratio. So it's like pi is the Greek, pi for us is a number, right? But at the end of the day, pi is just lowercase. What? These are Greek letters, right? These are Greek. So this phi actually represents a number as well. But we're using it as a variable, not as the numerical. Wait, hold on. This might be loud.
Phi.
Whoa, shit. Damn. Really? Tell us how you feel.
Phi. Phi.
That's not definitive. I hear phi as much as I hear phi. Really? You've heard? I'm the first one?
I've only heard it as phi before.
Okay, the Greek word phi is pronounced with a long E. Look, the Greek word phi is pronounced with a long E sound, like phi. The English name, Greek, blah, 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 right? But I hear it both ways. I mean, like in my mathematical studies, I had professors who would call it phi and other ones that would call it phi. So I just kind of mix it up. Sometimes I say phi, sometimes I say phi, faux fum, right? All right, let's get to a problem. Right into it. Holy shit, look at that. Look at that integram. That looks terrible. Okay, we're integrating over the solid E. What is the E? E is the region in the first octant between the spheres of radius 4 and 9. See if you can visualize that. We're in the first octant. You all remember what octants are, right? First octant is like the first quadrant with Z positive, so it's like everything in here. All this. And it's the region between those two spheres. One has a radius of 4 and the other one has a radius of 9. Sphere of radius 4 is curved, right? It's curved in. Yeah. I can stand there and move my hands around all I want. This is better, yes? Yeah, like a cantaloupe slice, exactly. Yeah, that one I definitely, I don't know why it's so damn zoomed in. Oh, because. There we go. There it is. First octant, sphere with a radius of 4, sphere of a radius 9. It's everything in between. Well, that is a perfect spherical coordinate rectangle, isn't it? What's your phi between? What's your phi between? 0 and pi over 2. 0 and pi over 2. So phi (0) and pi over 2. And then what should we look at next? You want to do theta? Theta is between first octant, so 0 to pi over 2 again, right? 0 to pi over 2 is theta. That's 0 to pi over 2. And then rho is your distance out, right? Which 4 and 9. I think of spherical a little bit, well, sometimes like if I had a string, right? If I had a string attached to my hand, the other side I had like a bird, a pet bird, okay, that enjoyed doing this, all right? And I, let the bird go. It would get to where the string is taut. And then, it could go this way, right? Theta. Phi. And then you have theta, right? And then in that case, the radius would be, I guess if it stayed out, then it would just do a shell, right? And it would look like the inner piece of this, right? It would be like that. And then if I let out more string, then it could fly out into anywhere in this region. Yeah, make kind of sense? There's different ways to look at it. All right. Are we done? No, we haven't even set it up, right? Let's set it up. Triple integral. All right. Our limits of integration aren't going to matter the order, right? Because they're all constant. 0 to pi over 2, 0 to pi over 2, 4 to 9. All right. E raised to the square root of x squared plus y squared plus z squared. Yeah, but remember, we said that there was a spherical conversion right there. That x squared plus y squared plus z squared equals rho squared. So I'm just going to put there rho squared, right? Square root of rho squared. Just rho. E to the rho. And then, yeah, you got to remember the new part, right? That used to be the r is now rho squared sine phi. Got to put that in because you went from Cartesian to spherical. And now the order of integration will go d. Yeah, this is our restrictions on rho. So d rho, d. And since these are the same numbers, it doesn't matter really. But I'll go theta then phi. There it is. You'd integrate with respect to rho first, wouldn't you? You could with respect to rho first? If you do it with respect to rho, that's a constant, right? How would you integrate that? Rho squared, what's that? What? Integration by parts. Yeah. That'd be integration by parts. Twice, because you'd have to get the rho squared to go away. But it can be done, and you know what? So can a computer. A computer can do it as well. There we go. Wait a minute. Why did I do 2 and 3? Hold on. Yeah, I must have typed it in wrong when I did it initially. Yeah, obviously, yes, because I'm giving you the radius. So this should be, what, 4? And this should be 9. Oh, surprise. Oops. What the heck just happened? 9. Oh, but I fixed it. I fixed it here, though. I must have caught this, but I never fixed it there. Right? I fixed it right here. 4 to 9. E to the r squared sine phi. And then you get this crazy thing, and then that comes out to be 82,000, whatever. No, 826,000. Who cares? All right, there we go. 3 problems for you to do. So this is just really the purpose of these 2 sections is just to get you acquainted with how triple integrals work in these 2 new coordinate systems. I encourage you on your homework to just use the computer to get the answers. Okay, I don't care about you grinding out these answers by hand, but make sure you can get the integrals set up properly, which means you need to know what the regions look like. Yeah? All right. This should be the last section of chapter 12. Let me verify. Yep, this is it. Okay, so we need to have a discussion here about this section. Section's called change of variables. And what we've been doing is exactly this. When we went from Cartesian to polar, right, in two-dimensional space, that was a change of variables. We went from things that involved x and y to r and theta. And then here, with spherical, we went from x, y, z to rho, phi, and theta, right? So those are called changes of variables. And mathematicians, we have to figure out ways to do that properly. And we know that when you go from Cartesian to polar, you have to include an r in there. And when you go from, well, for the integral, you have to include an r. And then when you go from Cartesian to spherical, you have to include this weird rho squared sine phi. Why, right? Why? So this section talks about how we actually do that. And as many years as I've been teaching this class, the more I try and explain it, the more confusing it seems to get for students. And there's a reason why. The reason is that in order to prove to you the formula I'm going to show you, you need to understand how to draw a surface with a vector function. Now, the only thing we know how to do in this class right now is to draw curves with vector functions. Go back to chapter 10, and I could give you a function r of t equals, and then I could give you either a two-dimensional vector, or I could give you a three-dimensional vector function. And this will draw curves, either on a flat sheet of paper or in three-dimensional space, right? To understand the proof of why this formula that I want to show you, to prove it to you, you have to know that there are actually other functions where it's a vector function, but instead of taking in one input, it's going to take in two inputs. So it'll become like, I don't know, s and t goes in. And then it spits back a vector in three-dimensional space. And these were curves, right? These were curves. This is a surface. We haven't studied these. We will. They're in chapter 13. So I think when the book tries to explain in chapter 12, section 8, when they try and explain where this formula comes from, there's a little bit of hand waving that goes on because they realize you haven't seen this yet. So you can't be completely comfortable with it, but they can give you some basic geometry idea. So in my years of teaching this, I've tried different ways. I've tried to really get you to see the geometry and make the formula make sense. I've just said, hey, here's the formula. Let's just use it. I've been all over the place with it. And I continue to go back to, let's not try and explain it. Because it just, we eat up a lot of time, and then at the end, there's a lot of confusion. I can give you a rough sketch of it. If you all want, I can give you like a rough sketch, but you're going to have to just take some things on faith. What do y'all want? Straight to the formula, rough sketch, or who wants a rough sketch? Okay, that's enough. We'll do a rough sketch. It's going to be real rough, though, okay? It's going to be real rough. This right here is the polar conversion. So the right side is Cartesian, okay? This is Cartesian, x, y, right? X, y. And then over here, you have theta and r. And so what we want to do is we want to see, is there a way, see, I'm going to start bogging myself down, but I'll try. We want to see, is there a way that you can approximate this red, right? Like this area and that area are not the same, right? They're different shapes. But is there a way to somehow take this and scale it somehow to become this? Like there's some sort of scaling that has to happen here for these two to go from here to here. There's some sort of scaling. Whatever this area is, I need to multiply it by something to make it equivalent to that. So the way to do this is to realize that if this was a surface, excuse me, then we can come up with a vector that goes from here to here and a vector that goes from here to here. And the red dotted box, well, actually it's not a box, it's a parallelogram. We know how to find the area of that parallelogram back from when we were learning about cross products of vectors. And when you take the cross product of two vectors and take the magnitude, you get the area of the parallelogram formed by the two. So I need to somehow figure out what these vectors are and then cross them and take the magnitude, and that will give me what I need to scale by. Now, what are these vectors? Well, again, this is where you have to think about a surface. If you're on a surface, imagine you're on a surface, three-dimensional space. If you're on a surface, in one direction is like a partial derivative in one direction, and then in another direction, it's a partial derivative in that direction. And so that's what these two are. These are the partial derivatives of the vectors. And then there's this delta u, delta v, which basically scales those two vectors back. And then when you go to the infinitesimal and take the limit, you basically the little red shape becomes a box. So that's the rough sketch that I can give you. That the area over here, in order to get from here to here, we somehow need to take a cross product, the magnitude of a cross product of these two vectors. And those vectors involve partial derivatives of something. Sorry, that's the best you're going to get. Okay? That's the best you're going to get. Because right now we just don't have, we don't know what surfaces with vector functions look like yet. So I'm going to scroll all the way down to this right here. This is it. So what we're looking at here, this formula, is for double integrals only, right? Double integrals only. It says, and I think I want to give myself a little room down here so that I can write. This formula says that if you have a double integral over some region D of f of xy dA, and then you want to switch that. You want to switch that by somehow converting your x to some new function. X is, the way we write it is this, x is now becoming some function of u and v, and your y is now becoming some function of u and v as well. Then the way you convert that is you set up the double integral over this new surface S in this new space. Then you'll have your function f evaluated at that new u and v, and then the y of u and v. And then you'll have to multiply that by the magnitude of this thing right here, which is called the Jacobian determinant, which is partial x with respect to u times partial y with respect to v minus, you got it there, right? Partial x with respect to v, I'm going to run out of room, partial y with respect to u. Okay, so look, it's saying if you're coming over here and over here, whatever system you're in, this doesn't even have to be Cartesian, but let's just start with Cartesian. If you come in here and you've got some region in here, right, which we call D, and you want to do a double integral over that region, and you look at it, you're like, this sucks. This region is no good for this coordinate system. Then you're welcome to change the variables from x and y to two new variables, u and v. You're welcome to do that. But when you do that, your function now needs to be evaluated at your new values of x and y. whatever they are in terms of u and v, whatever this is in terms of u and v, and then you have to include this thing. This is the cross product of two vectors and their magnitude. That's what this is right here. So, yeah, I can't get into it. I don't want to. So this is what we get, right? So I want you to see that this is exactly what polar is. I'm going to do it in purple. What is our conversion for polar? For polar, we say x is equal to what? R cosine theta, and y is equal to r sine theta, right? So we've converted x and y to now something that involves what two variables? R and theta. This formula has u and v, right? So what I'm going to do is I'm going to ask you, just for the sake of explaining, for us to not do that, let's say that x was equal to, let's say u sine v, and then y was u, sorry, that was cosine, sorry. U cosine v and u sine v. So what I'm doing is instead of using r, I'm using u, and instead of using theta, I'm using v. Those are like dummy variables. This is still a polar conversion, isn't it? Right? Still polar. That's an S. Okay? Okay, so what will happen is in our new integral, we'll have this region will look different. S will look different over here because we've converted. This will be the original function. This will be replaced with what? U cosine v, and this will be replaced with u sine v. And now we have to do this computation. Let's do it. I want to do this part right here. All right, what is the partial of x with respect to u? So what's partial of this with respect to u? Cosine v. Oh, why am I doing that? Cosine v times partial y with respect to v. So what's partial of this with respect to v? U cosine v. Okay, minus partial of x with respect to v. X with respect to v. Negative u sine v. And then partial of y with respect to u. What is it? U cosine. What? Sine v. Sine v. That right there is the partial of y with respect to u. And so what you wind up getting is u cosine squared v minus minus is plus u sine squared v. Magnitude. And then you can pull a u out of both of these, and you'll have sine squared plus cosine squared, which is 1. So you wind up getting the magnitude of u, which is just u,